this course, we'll focus on EVPN L3VPNv4 over SRv6 policy. L3VPNv4 indicates that IPv4 is deployed between a PE and a CE, and the CE carries IPv4 services. From the perspective of the control plane, EVPN is a BGP-specific extension in comparison with conventional BGP L3VPNv4, even though it appears to be a service type. Let's take an example of 5 devices to describe the detailed configuration and verification processes in the EVPN L3VPNv4 over SRv6 policy scenario. P1, the P, and P2 all belong to AS100 and reside on the public network of a carrier. C1 and C2 are connected to customer networks. A bidirectional SRv6 policy needs to be established between P1 and P2 to carry the IPv4 services on the CEs. The configuration roadmap is as follows. First, enable ECs on P1, the P, and P2 to achieve basic route reachability. Second, configure an SRv6 policy between P1 and P2. Third, configure a BGP EVPN peer relationship between P1 and P2 to advertise routes between C1 and C2. The first step involves configuring ECs to achieve basic route reachability. EC's configuration consists of global configuration and interface-specific configuration. In this step, loopback interface routes are used to establish BGP EVPN peer relationships and configure source addresses for SRv6 encapsulation. The next step is to perform basic SRv6 configuration. This involves enabling SRv6 globally, configuring a source address for SRv6 encapsulation, creating a locator, and configuring seeds in the locator range. Path programming needs to use AND seeds representing nodes, and AND.x seeds representing adjacencies. In this example, we configure an AND.x seed to represent the adjacency from P1 to the P. The outbound interface is GE101, and the next hop is the address of the specified interface on the P. In SRv6 policy scenarios, menu seed configuration is recommended, so we use this method in this example. Then we can use the auto seed disable parameter to disable ECs from dynamically generating seeds. After EC's configuration and basic SRv6 configuration are complete, we can check EC's routes on the PEs. The command output in this example shows that P1 has learned the locator routes of the P and P2. The P has also learned locator routes. Because seeds are allocated within the locator range, they are routable on the devices. Based on the preceding configurations, P1 generates one AND.x seed for the adjacency from P1 to the P. The P generates two AND.x seeds, and the P2 generates one. These AND.x seeds can be combined to form an explicit path. Moving on, let's switch our focus to SRv6 policy configuration, which mainly involves configuring segment list-based explicit paths, specifying each involved hop, configuring an endpoint and color value for the policy, and configuring candidate paths to reference the configured segment lists. The configurations on P2 are similar. After configuring the SRv6 policy, let's check its connectivity by performing a ping operation on P1 and P2. If the ping succeeds, the previous configuration is successful. After completing SRv6 configurations, let's look at BGP-related configurations. Specifically, we need to configure CE access and specify an AND.DT4 seed for the VPN instance on each PE. Then establish eBGP peer relationships between the PEs and the CEs. In addition, we need to configure an AND.DT4 seed for the VPN instance on the PE. AND.DT4 seeds generated on the PEs are added to local seed tables. According to the tables, we can see that each AND.DT4 seed is bound to a VPN instance. Next, we need to establish a BGP EVPN peer relationship between the PEs to transmit routing information between the CEs. Let's take a look at some key commands. The first command enables the device to advertise the routes of the specified VPN instance as EVPN Type 5 IP prefix routes to the peer PE through the BGP EVPN peer relationship. The second command is used to add the seed attribute to the BGP EVPN routes to be advertised. The third command is used to perform route recursion based on the seed attribute carried by EVPN routes. SRv6 policies are preferentially selected for route recursion. The best effort keyword is optional. If SRv6 BE is configured on the network, SRv6 BE paths can be used as best effort ones in the case of SRv6 policy failures. The last command is used to enable the device to advertise EVPN routes carrying SRv6 encapsulation attributes to its peer. Next, we need to configure route recursion to SRv6 policies. A route can recurse to an SRv6 policy only when the color and next hop of the route match the color and endpoint of the policy. To configure the route coloring function, we first need to define a route policy and specify the color attribute 0:101. The value 0, which is fixed, indicates the color flag. The color value is 101. Route recursion is allowed only when the color value of the route is the same as that of the SRv6 policy. Then let's apply the route policy to BGP routes to be received. The route policy can also be applied to the BGP routes to be advertised, but we need to configure the device to advertise extended community attributes in this case. Finally, we need to configure and apply a tunnel policy on the PEs to import the IPv4 traffic on the CEs. The configuration mainly includes the following steps. First, create a tunnel policy and specify the tunnel type to be selected and the number of the tunnels that can participate in load balancing. Second, apply the tunnel policy to the corresponding EVPN L3VPN instance. After a BGP EVPN peer relationship is established, the devices advertise update messages carrying path attributes and an LRI. Next, let's take a closer look at this type of message. A BGP update message carries multiple path attributes, including some common ones. In this scenario, the message also carries the extended communities attribute with RT information, the BGP prefix seed attribute with end.dd4 seed information, and an LRI. According to the LRI, we can see that the L2VPN EVPN address family is used here. The route type is EVPN Type 5. The RD, route prefix, and prefix length information are also carried. Because we configured an import route policy, the route does not carry any color value. However, if we configure an export route policy, the color attribute will be carried. Now, let's look at the BGP EVPN routing table. We can see that the BGP EVPN routing table on P1 already contains the route of CE2. As for the route format, the digit 0 is a fixed value of the EVPN Type 5 route. The middle part indicates the address prefix, and the last part indicates the mask length. The next hop is the loopback address of P2. According to the detailed route information, the route carries a color value and a prefix seed, which is the end.dd4 seed of the VPN instance on P2. The route type is Type 5. Next, let's verify the configuration. We can see that the preferred BGP route on a PE first enters the IP routing table of the corresponding VPN instance. The outbound interface of the route on CE2 is displayed as policy 1, indicating that the route has successfully recursed to the SRv6 policy. P1 then advertises the route to CE1 through the BGP peer relationship. The route first enters the BGP routing table. After being preferentially selected by BGP, it enters the IP routing table. In the IP routing table, we can see that this route is learned through eBGP. Finally, let's ping CE2 from CE1. If the ping succeeds, the configuration is successful. That's all about the implementation of EVPN L3VPNv4 over SRv6 policy in the control plane. Next, let's see how packets are encapsulated during forwarding. Now, let's look at the encapsulation process of packets forwarded from CE1 to CE2. CE1 first initiates a ping operation by sending an ICMP request packet, for which IPv4 encapsulation is performed, using CE1's address as the source address and CE2's address as the destination address. After receiving the packet from CE1, P1 performs SRv6 encapsulation by adding an SRh into the packet. In contrast, the reply packet is transmitted over an SRv6 BE path without carrying any SRh. That's all about the encapsulation of packets in an EVPN L3VPNv4 over SRv6 policy scenario. As we reach the end of this course, let's summarize the route advertisement and data forwarding processes in this scenario. Taking route advertisement from CE1 to CE2 as an example, the advertisement process mainly consists of 5 steps. First, the routes on CE1 are advertised to P1 through the eBGP peer relationship. The routes in the IP routing table can be imported to the BGP routing table before being advertised. The BGP routes on CE1 are then advertised and imported to the routing table of the specified VPN instance on P1. Second, after the advertised L3VPN EVPN command is run on P1, the routes of the VPN instance become EVPN routes and enter the EVPN routing table. Third, after a BGP EVPN peer relationship is established between P1 and P2, EVPN Type 5 IP prefix routes are advertised through the peer relationship. Fourth, the BGP EVPN routes are automatically linked to the VPN instance based on the RTs carried. Fifth, after the VPN instance on P2 learns routes, it advertises the routes to the BGP routing table of CE2 through the eBGP peer relationship. Then, the preferred BGP route enters the IP routing table for forwarding. Now, let's look at the data forwarding process. Assume that CE1 sends a packet. First, CE1 performs IPv4 encapsulation on the original IPv4 packet and sends the packet to P1 through a specified interface. Second, after receiving the packet from the VPN instance bound to a specified interface, P1 searches the routing table of the VPN instance according to the destination address and finds the associated next hop information. P1 then encapsulates an SRh and the end.dt4 seed into the packet. In the forwarding phase, according to the instruction bound to the first end.x seed, P1 decrements the SL value by 1, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the end.x seed. Third, the P searches the local seed table according to the outer destination address and finds a matching end.x seed. According to the instruction bound to the second end.x seed, the P decrements the SL value by 1, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the end.x seed. Fourth, P2 searches the local seed table according to the outer destination address and finds a matching end.dt4 seed. According to the instruction bound to the end.dt4 seed, P2 removes the IPv6 header, finds a VPN instance matching the seed, searches the IPv4 routing table of the VPN instance, and then forwards the packet. That's all for this course on EVPN L3VPNv4 over SRv6 policy. Thank you for watching.